So, if you've ever worked with distributed systems, you've definitely heard of the CAP theorem. It's like the foundation of everything. But it doesn't really tell the whole story. Today, we're going to dive into its powerful extension, the PACELC theorem, which gives us a much more complete picture of the trade-offs we're constantly making. Right, we all know the drill with CAP. It tells us that when there's a network partition, when your servers can't talk to each other, a system has to make a tough choice. You can have consistency, where everyone sees the same latest data, or you can have availability, where the system stays up and running even if some of the data might be a little stale. It's absolutely fundamental, but it leaves this one massive, glaring question completely unanswered. And this is the crucial point. CAP is all about what happens when things go wrong, right? When the network breaks. But what about all the other times? What about when everything is running perfectly fine? What trade-offs are we making during normal, everyday operations? That's the huge gap in the story that CAP just doesn't address. Well, the answer to that question is the PACELC theorem. This is what gives us the full picture, covering not just those failure states, but normal operation too. Okay, so what is PACELC? Let's break down this acronym. It's actually pretty straightforward. It says, if a partition happens, you have to trade off between availability and consistency. Sound familiar? That's the PAC part, and it's basically the CAP theorem. But, and here's the key, else, when there is no partition, you face a totally different trade-off. It's between latency, how fast your system is, and consistency. That's the LC part. So yeah, that first half, PAC, that's not new. If you get the CAP theorem, you already understand this. It's just confirming that fundamental choice you're forced to make during a network failure. No surprises there. The real game changer here is the second half, ELC, else. Latency versus consistency. This is the part that CAP is totally silent on. It forces us to think about the trade-offs we're making every single second our system is online and healthy. Do we want our responses to be lightning fast, or do we want to absolutely guarantee they have the latest version of the data? You can't always have both. So you can think of your system as living in two different worlds. When there's a partition, it's a battle between being online, that's availability, and being correct, that's consistency. But during normal happy path operation, it's a battle between being fast, latency, and again, being correct. Did you notice? Consistency is the one thing you're always trading against. This all sounds great in theory, but how does it actually play out in the systems we use every single day? Let's get practical and see how real-world databases actually make these PACELC choices. And of course, there is no single right answer here. The choice a system makes depends completely on what it's built for. I mean, a system designed for high-speed financial transactions is going to prioritize very differently than one built for, say, massive data analytics. These PACELC classifications aren't accidents. They are deliberate, critical design decisions. Okay, let's look at some big names. You've got systems like DynamoDB and Cassandra. They are what we call PA/EL. They prioritize availability during a partition and low latency during normal operation. Think about a social media feed. You'd much rather it be fast and always available than wait for a perfectly up-to-the-millisecond like count. Then, way on the other end of the spectrum, you have things like Bigtable and HBase. They are PC/EC. They always choose consistency no matter what. This is for things like bank ledgers or billing systems where the data absolutely must be correct, even if it means a user has to wait a bit longer or sees an error during a network hiccup. And then you get these interesting hybrids like MongoDB, which is PA/EC. It chooses availability during a partition so it stays online, but it prioritizes consistency during normal times, aiming for correctness when everything is healthy. So what's the big takeaway from all of this? It's that designing systems is about a constant series of trade-offs, not just for those moments when things go wrong. Just remember this, the CAP theorem, that's for emergencies. PACELC, on the other hand, that's for all the time. And that means, as a developer or an architect, you are always, consciously or not, making a choice between speed and correctness, even when your system is perfectly healthy and running smoothly. We started with this exact question. And as you can see, PACELC gives us the definitive answer. It fills that silence. It forces us to confront this trade-off between latency and consistency, proving that even in a perfect world, compromises are just unavoidable when you're building distributed systems. And that leaves us with one final thought, something for you to consider for your own work. Forget about failures for a second. On a perfect day, when all your servers are humming along beautifully, What does your application, and more importantly, what do your users truly value more? Getting an answer instantly or getting the most perfectly correct answer possible? Because the answer to that question, well, that defines your system.